So if you remember what we did yesterday, we're factoring polynomials, which takes them from their traditional standard form, that's a simplified standard form, and converting it to something that is then not in standard form anymore. You're actually taking something that's already simplified, and doing the opposite. Factoring it takes it and makes it unsimplified. So in order to simplify polynomials, you really have to look at each one and problem solve and almost go through a checklist, like, can I do this? And if not, here's the next thing I should try. So in looking at these examples in this section are different than the examples we did yesterday. If you remember the examples we did yesterday, we can kind of look at like one of them from yesterday. Let's just look at the first one, the factor the polynomial number 1, 12x squared plus 28xy squared. When I look at this polynomial, I look for the greatest common factor first to see if there's anything I can do to pull out of all of those terms. So I'm looking at 12 and 28. The greatest common factor between 12 and 28 is 4, and I'm looking at the x squared, the x and y squared. I can also take an x out of both of those terms. So the GCF would be 4x, and then I would rewrite whatever would be left over on the inside of the parentheses. That's using the GCF. So when I go down to example 2, and I'm looking at this polynomial, 4x cubed minus 8x squared plus 3x minus 6, I'm looking first at the coefficients. That means I'm looking at 4, this negative 8, 3, and negative 6, and I can't take a number out of any of those coefficients. So I can't pull a factor of 2 out of all of them. I can't pull a factor of 3. They don't have anything in common. They're considered relatively prime numbers when you're looking at them all together because the only factor they share is 1, and when you take 1 out of a number, it doesn't change anything. So a number can't be taken out, and then when I look at the variables as well, this one has a third power x, this is second power of x, first power of x, but this one doesn't have one, so I'm stuck. I can't use the GCF factoring tool in this problem, which is why this is under a different type of an example. This example is factoring by grouping. And this is why these problems are difficult, because every single one is going to be completely different. And you just have to kind of problem solve through the different types of factoring processes and then figure out which one will work, and you'll finally come to one. So here's a new type of way to factor a polynomial, and it's factoring by grouping. So this method is often used when polynomials have 4 terms. It doesn't have to be this case. Sometimes you would use this if it doesn't have 4 terms. Sometimes, like if it has 8 terms, you can do it. I mean, it doesn't have to be 4 terms, but if you see a polynomial that has 4 terms that can't be simplified and there's no GCF you can take out, meaning you can't take any numbers out or any variables out of all of the 4 terms, then you probably can factor by grouping. And these problems are specifically created so you can factor by grouping. Because sometimes things are just not factorable, but all 3 of these can be factored by grouping. So this is a very interesting way to factor polynomials. What you do is you basically split the polynomial into 2 parts. So I like to honestly just like draw a line down the center so that there's 2 terms on the left-hand side of the line and 2 terms on the right-hand side of the line. Once you do that, then you're looking at these terms separately, and you're going to factor each little pair by the GCF method. So that means I'm looking at 4x to the 3rd power and the negative 8x squared, and I'm going to factor that separately, and then I'm going to factor 3x minus 6 separately. So if I'm looking at 4 and 8, the GCF of 4 and 8 is 4, and then x to the 3rd power is 3x's, x times x times x squared is 2x's, x times x. So the greatest number of x's I can take out of both of those terms is x squared. Once I take out the GCF, I insert the parentheses here and put in whatever's left over to make that still equal to 4x to the 3rd power minus 8x squared. And for the first term, since I'm taking a 4 out of the 4, and I'm taking x squared out of x to the 3rd power, the only thing that's left is an x. And then for the second term, this is going to be a minus sign because the minus in the original problem. And I'm taking out a 4 from 8, and it's 8x squared. I'm taking all the x's out of it. So what number would I have to put here to the right of the minus sign? A 2, exactly. So what I did was I factored just those two terms to the left, and I factored that to be 4x squared times x minus 2. I'm going to do the same process for the next two terms. So now I'm looking at the 3x and this minus 6 here. Well, I don't have any variables that I can take out of both, but the largest number I can take out a factor of 3. So I can take a factor of 3 out of the first term and the second term, and I'll be left with x minus 2. Now, because this is a plus sign here, I can put a plus sign right here to combine these two things together. So what I did was I split up the polynomial into two halves. So I split it right down the middle. I factored the left-hand side and I factored the right-hand side. Now, these polynomials are specifically created so this can happen. If you're looking closely at the factored form, see how you have the same thing here as you do here? It ended up being that when you factored it, inside of the parentheses, you actually got the same exact term, x minus 2 in both. What happens with that is using like a commutative property, you can actually pull out the x minus 2 and what's left over here, which is the 4x plus 3. And you can put this into its own set of parentheses, 4x squared, I meant to say x squared, sorry, plus 3 in parentheses, and that whole thing can be multiplied by the x minus 2. So this is like kind of a confusing idea. But when you have the same thing, like a certain number multiplied by, like let's just call it variable a. So anything multiplied by a and anything else multiplied by a, you can take those two other numbers, multiply them together, and then all multiply them by a as well, and you're not changing anything. It's basically like the commutative property. You can move things around in multiplication and still get the same answer. So what happened is because these x minus 2's were the same, I basically just pulled out the 4x squared plus 3 and put that in its own set of parentheses, and that will all be multiplied by x minus 2. Since 4x squared is being multiplied by x minus 2, and 3 is being multiplied by x minus 2, I could put 4x squared plus 3 in its own set of parentheses, which is going to all be multiplied by x minus 2. Hope that makes sense. So when I go to just verify that this is true, I could quickly FOIL this out. 4x squared times x is 4x to the third power. 4x squared times negative 2 is negative 8x squared. 3 times x is 3x. 3 times negative 2 is negative 6. Looking at the original problem, that is exactly what it was to start, so I know that I have the correct factored answer, which means that this is the factored answer, and this is factored completely. So when we're solving these problems, we want to factor each one completely. I wish the directions said this. Because if you look at this part right here, technically this is factored because you took out a GCF of each little part. But the factored completely part would mean that you actually then have the final answer with just the two sets of parentheses with the binomial times the other binomial. So looking at number 2, the first thing you should do is look at the coefficients. 2, negative 3, 8, negative 12. I can't take a GCF out of any of those. Then look at the x's, x to the third power, x squared, x, and there's no x. I can't take any x's out either. So because it's 4 terms, because there's no GCF I can take out of all 4 terms, then what I'm going to do is try this factoring by grouping. I take a line and I split up the polynomial in half, and I factor the first half and second half completely separately. And then what will happen is you'll see the similarities in the factoring, and you can then rewrite it like this. So looking at 2x to the third power minus 3x squared, I can't pull out anything from 2 or 3, so those will stay, but I can take out x squared from both of these terms. So I'm going to take out x squared, and on the left-hand side, I'm going to be left with 2x minus 3 when I take x squared from both of those terms out. And then on the right-hand side, it's 8x minus 12. I can't take any x's out, but the largest number I can take out is 4. So I'm going to take a 4 out of the 8x minus 12. And when I do that, I'll be left with 2x, since 8x divided by 4 is 2x. And then 12 divided by 4 will be this minus 3 here. then once you do that, you should be pleasantly surprised each time to see the same thing here and here. And you can put this plus sign here. So because we have a 2x minus 3 in both positions, what we can do is rewrite it. And it doesn't matter the order. You can either rewrite it as 2x minus 3 times, and what you multiply it by is this binomial in its own separate parentheses by x squared plus 4. Or you can always switch the order. It doesn't matter the order. It's correct either way. X squared plus 4 times 2x minus 3 is still correct as well. Okay, so that would be the final answer factored completely. And then moving down to the last one here on this page before you try a couple on your own, x to the third power minus 5x squared plus x minus 5. Checking for GCF, I can't do it. There's no number I can take out of all of the terms. There's no variable I can take out of all of the terms. The first step would then be to split it in half, factor both sides separately. X to the third power minus 5x squared. I can't take a constant number out, but I can take x to the second power out of both terms. When I do that, x to the third power divided by x squared, you're going to be left with an x here, minus 5. Since when we take out x squared from 5x squared, you're just going to be left with the minus 5 there. And then what's interesting about this one on the right-hand side, and sometimes this does happen, if you look at x minus 5, x minus 5 really can't be factored. There's no number or variable that can be taken out from both. But in order to factor this completely, in order to use this method, if something cannot be factored, you should try taking out a factor of 1. So I'm going to take a factor of 1 out of the x minus 5, and I literally will just get x minus 5 in there. When I do that, I can actually still see that it will work because both of these sets of parentheses here have the x minus 5. So then altogether, you can rewrite it as x squared plus 1 times x minus 5. Or in the opposite order, you can write x minus 5 times x squared plus 1. All right, there's 2 practice problems on the next page, on page 16. So please take a few minutes, try these 2, ask me questions as they come up, and then we'll go over them in like 4 minutes or so. right, so for these two problems, first thing you should do, look at coefficients, 1, 2, 1, 2. I can't take anything out. Look at variables. I can't take anything out. It's 4 terms, so let's try and split it in half and try factoring both sides separately. Well, I feel like a lot of these have the same thing you take out. It's not always going to be this way, but the only thing you can take out of both of these is x squared. When you do that, you'll be left with an x plus 2 on this side. And on the right-hand side, x plus 2 really can be factored, but because of this method, you have to take something out. So I'm going to take a 1 out of x plus 2, and I'm left with x plus 2. Once I do that, I can then see that I have the x plus 2 in both parentheses, which means I can then rewrite this whole thing as x squared plus 1 all times x plus 2, or the other way, x plus 2 all times x squared plus 1. So like when we get to our next test, if it's going to be one of the ones that grades it on its own, I will have both variations just so you know that either way it's correct. The order does not matter. Okay, and then number 2, using that same method, I can't take anything out number-wise or variable-wise. So when I go to factor this separately, drawing the line, for this one I can take out 3x squared from both, and I'm going to be left with 1x here, and then plus 2. And then on this side, I can take out 5 from both. I'm left with x plus 2. The way to really tell that your answer is correct is by seeing this. If this happens, you know your answer is right. This only will work in this particular, if these problems are set up this way, it will only work out that these numbers on the inside are the same. So your final answer is 3x squared plus 5, all times x plus 2, or the other way. You can always take the time, if you want, to just multiply everything out using FOILing in this case, since this is a binomial times a binomial. If you multiply first, outer, inner, last, and verify that it equals the original problem, you know that you factored it correctly. In example 3, these problems are going to get a little bit more difficult, and unfortunately what's weird about these types of problems is factoring a polynomial is different in every single situation. Like even when I see something like this, I'm like, all right, I have to think about like what can I do? I always start with GCF. Can I take any numbers or variables out? And if I can't do that, then I kind of just like go down the line and see, well, what else can I try? There's no really like way to tell unless you start looking for the patterns of what these polynomials look like. So in these examples, these are called factoring special products, and this happens when you have something like x squared minus 64, which is both terms are actually considered squares. So I should first talk about what that means. So a number that is square it means that if you take the square root of that number, it equals an integer. So, for example, if you take 1, I'll just write it over here. 1 squared equals 1, 2 squared equals 4, 3 squared equals 9, 4 squared equals 16, 5 squared, I mean, I do this forever. But I'm just basically taking integers and I'm squaring them. I'll go up to 100. When I take integers like 1, 2, 3, 4, and so on, and I square them, then these numbers here, what they equal, are considered perfect squares. When you take the square root of perfect squares, it equals an integer. For example, the square root of 1 equals 1, since 1 times 1 is 1. The square root of 4 is equal to 2, since 2 times 2 is 4, and so on. So when we're factoring these problems here, the first thing when you're looking at like what process you should go and what process you should try, you should notice that this is an x squared, meaning that's a perfect square. And then this 64 here is also a perfect square. I see 64 here in that line of perfect squares. So because both of these are considered perfect squares, then we can factor this by using this idea here, that if you have 2 perfect squares that are being subtracted, what ends up happening is when you go to factor it, it's going to end up being the sum and difference of the two same things. So this is kind of weird, especially doing this first before we try the next section, which is trinomials. But if you see this, what's going to end up happening is you're going to have a binomial times another binomial. And since this first term here is x squared, we're going to need an x here and an x here, so that when you went to multiply it, it would equal x times x is x squared. And then one of them is going to be a plus sign, one of them is going to be a minus sign. And it's going to be the square root of that next number that's the perfect square. The square root of 64 is 8. So you're going to have plus 8 and minus 8 here. That's going to be the factored form for letter A, which is just a little bit weird doing this without doing the next section first. So when I look at letter B, same type of idea. Before I even do that, I can also just quickly verify x times x is x squared. X times negative 8 is negative 8x. 8 times x is 8x. And 8 times negative 8 is negative 64. You can see how the negative 8x and the positive 8x cancel out. That's where we get the x squared minus 64 from. All right? So when I look at letter B, I try to see and find any GCFs I can take out. I can't. And then I go down the line, and I can't take any variables. So then the next thing I'm going to think about is, okay, let me look at the numbers. This is x squared minus 9. These are both perfect squares. This process is called factoring the difference of two squares. What ends up happening is you're going to have an x here, an x here. It's going to be plus and minus, and the numbers are going to be the same in both. It's going to be the square root of whatever that second perfect square is. Square root of 9 is 3. So it's going to end up being x plus 3 times x minus 3. These are called special products because the middle terms end up canceling out. That's why when you go to factor it, it looks like it really can't be factored, but that's because the middle term, the terms go away since they are opposite numbers. Okay. So as we move on to the next ones, it's going to get a little bit more difficult because now we are going to have coefficients in front of these variables as well. So when we have these types of numbers, or when we have numbers in front of the variables, we're going to first look at the coefficients and see if there are any GCFs I can take out. Like once I see 49 and 81, I'm thinking, but the factors of 49, thinking about the factors of 81, they don't share any common factors. So I can't take out like a factor of 2 from both. I can't take out like a factor of 4. So now I'm thinking about this method, the special products. I'm looking to see, are these perfect squares? Well, 49 is a perfect square. X squared is a perfect square. 81 is a perfect square. Y squared is a perfect square. These are all perfect squares. The numbers I can see in this line, 49 is here, 81 is here, and then x squared is a perfect square because it's any number squared, which is a perfect square, and same thing with y squared. So then when I go to set this up, it's just going to be a little bit different, kind of the same. You're going to have a binomial times a binomial, but instead of having just like an x here and here, we're going to have two things. We're going to have x's and we're going to have y's. One's going to be plus, one's going to be minus. And we're going to need numbers in front of the variables as well. So we're going to have to take the square root of 49, which is 7. So I'm going to need a 7 here and a 7 here. Because 7x times 7x is 49x squared. And then we're going to need a number in front of the y's. It's going to be 9, since 9 squared is 81. So what we end up getting is the same thing but the opposite. This is definitely more difficult to understand. We have 7x plus 9y in one binomial times 7x minus 9y. If I go to multiply this out, the middle terms cancel out. I'm only left with the first and the last, which would be 7x times 7x, which is 49x squared. And then the 9y times negative 9y will be minus 81y squared. All right, and I know these are weird, but we're going to keep going. The last one here in this section is, again, all perfect squares. 4 is a perfect square, x squared is a perfect square, 25 is a perfect square, y squared is a perfect square. So let's set this up. We're going to have like an x plus y and an x minus y. But we're going to have numbers in front of the x's and y's. What number do I need in front of the x's so that when it multiplies, it's 4x squared? What's the square root of 4? 2. So I'm going to need a 2 here and here. And then what about the 25?
5.
Yes. And then that would be your final answer. All right, and then the last thing for today before I'm going to have you guys try some practice on your own is even crazier than that one. Now we're looking at factoring the difference of 2 cubes. So now the next thing that you should be looking down the line, okay, I can't take a GCF out of x to the third power or 8. I'm looking at x to the third power. That's not a perfect square. 8 is not a perfect square. So there has to be something else. This doesn't have 4 terms, so I can't split it in half and factor both of them separately using the GCF. So here's another thing that you can do if you see something like this. And it's called factoring the sum of 2 cubes. So similar to perfect squares, we also have something called like cubed numbers. So if we take 1 to the third power, 2 to the third power, 3 to the third power, 4 to the third power, 5 to the third power, and I'll stop here at 6 to the third power. All of these answers are going to be considered like, I guess, perfect cubes. So 1 to the third power is 1 times 1 times 1, which is 1. So 1 is actually a perfect square and a perfect cube. 2 to the third power is 2 times 2 times 2, which is 8. Then we have 27, 64, 125, 216. These keep going, but I'm just going to stop there. These numbers right here are all considered, I guess we'll call them perfect cubes. I've never really heard it called perfect cubes, but why not? So when you're looking at these problems, similar to the perfect squares, now we're looking for cubed numbers. X to the third power is a perfect cube, and 8 is a perfect cube. Because anything to the third power will be a cube, and 8 is in this list here. So when this happens, this is just ridiculous. When this happens, here's how you factor this. So not this one. The sum of 2 perfect cubes, because this is a plus sign, you follow this idea here, and what happens is you're going to have like x plus y, which in this case is going to be the cube root of whatever this number is. The cube root means what times what equals 8, and that's going to be 2. So it's going to be like x plus 2 in parentheses, and then following along with this thing right here, then that it's going to turn into x squared minus 2x plus 4. And you might be wondering how I'm getting that. I'm literally just following along with what it's telling me to do.
Where's your 4?
So I got the 4 from because this is going to be considered, this is considered like x and this is considered y. So I got the 4 from taking the 2 and squaring it to get 4. I know this is super confusing. The next one's going to be very similar to this, except now we're going to follow this factoring idea, which is now just like the difference of 2 cubes. I know that we can use this because this is a perfect cube and this is a perfect cube. The cube root of 125 is 5, since 5 times 5 times 5 is 125. And what I'm doing is I'm basically following now this process. I don't have this memorized, even though I teach math. So I wouldn't expect you guys to necessarily memorize this one. This is not one of the ones that you might come up with on your own. But this one, to do it, if you needed to, it would be x minus 5 times x squared plus 5x plus 25. And we can always double check that this is correct by multiplying it out and verifying that it does equal that other one. Okay, so if we look at the next page here, there's some practice problems, and I was just quickly looking at the different ones we see here. In all of these examples, they're asking the correct directions that I would want it to say, factor them completely. So what I want you to do first is kind of forget about the craziness I just taught you with those last two types of problems, because those are not on here. I want you to just look for the GCF first, pull out any common factors that you see in both terms, and then see what's left, factor it even more if so. Sometimes if it has 4 terms, like in number 4, you should split it in half and factor both sides separately. And we don't have too much time. We have 5 minutes, so let's maybe just focus on getting 1 through 3 done, and then we'll go over the answers before we leave today. So try 1 through 3.